Hello everyone and welcome to this video where I'm going to explain how a TCP connection is handled by a Linux kernel. What I'm going to do in this experiment is that I'm going to have a client NCAT and a server NCAT, and these are just simple general purpose TCP client and server. Well, it can be also turned into a UDP client or a server that creates a connection to the other end, one NCAT to the other end, and you can pipe in any text that you type. And what I'm going to do is that I'm going to be tracing the server-side application when it receives the TCP SYN request and show you how that's being handled by the kernel, and then send a message back from the server to the client and see how that goes through the kernel on the server side. The tools that I'm going to be using here, well, it's obviously NCAT. NCAT is, you can download and install it here. It's, as I said, it's a simple tool to, it's something like a telnet, but with more features. The other tool that I'm going to use is LTTng. LTTng is a tool that you can use to, it's an open source tool. It's a tracer, so you can trace your kernel. There are different kinds of tracers. One of them is LTTng, which is a very nice match to another tool that I'm going to be using for the actual visualization and analysis, and that's called Tracecompass. This is also a Eclipse open source tool, and it provides you with a very nice analysis and visualizations of the traces that you collect with LTTng. The links to these tools are provided in the video description, and I'll create another video that would explain in detail how you do the tracing with LTTng, how you load up the trace in Tracecompass, and how you work with Tracecompass. But there's also a YouTube channel for Tracecompass by the guys from Ericsson, which have developed this, and you can refer to that as well. So these are the tools that I'll be using, and let's get on with the analysis then. Okay, so how I run the experiment is I basically have my NCAT here. So I'm just going to say NCAT listen. Now I've ran this command before. So I would say NCAT listen. Dash dash listen means this is the server on 192.168.1.105. That's the address of this server. That's the IP address of this server, that the address that I want to bind to. I want to bind the server to. This is the local address. And this is the local port that I'll be using to listen on. Okay, so I've done this before. And on the client side, I'm just going to run NCAT without the listen, 192.168.1.105, 5000. And then the connection is going to be set up and created. And then whatever I type in the terminal, in either the server or the client, is going to show up on the other side. So I've done this before. An interesting thing that I'm going to show you is I'm going to show you both the kernel trace using Tracecompass here. These are different parts of the code that get triggered in the kernel, which have a corresponding trace point. And at the same time, I've also collected a Wireshark trace or a packet trace of this interaction. So let's first look at the packet trace and see what we can find here. Well, obviously you can see that there is a TCP SYN request. This is the first request that's received from the remote side that would basically signal to the server that, hey, server, I want to connect to you. So this is where a new TCP connection is being requested from the client. So these are the packets that I'm receiving on my local machine, which is the server again. After that, my server responds with SYN ACK. So it basically acknowledges the SYN. Now you can see that the first SYN came from the address 1.102 to 1.105 TCP, right? The 1.102 is the client side, 1.105 is the server. The SYN ACK, the ACK to the SYN request, is basically going the other way around from 1.105 to 1.102. And the ports are 5000 is my server port, as you remember, is the server port that I bound NCAT to. And 14.61.5 is basically the client port, right? I didn't have any control on this one, just picked something. And then after that, an ACK is received from the client side, which I call the remote side here, which establishes the TCP connection. So this is the end of the three-way famous TCP handshake, as you may have heard of it. So after this, there's a packet going from the server 105 to the client, and it has a length of 6. So you can see that these other ones have a length of 0, but this has a length of 6. That's because I typed in hello and then pressed enter. So HELLO 5 and then 1 enter, 6 characters. So that's 6 bytes, which is like has the push flag set because normally TCP would wait for more data to gather and then send it. But this is because of the way that NCAT works, we want to push everything to the other side when an enter is pressed. So this is actually the push flag of TCP, right? And then that one is this data sent to the client side is ACKed by the client side. So you can see it comes from the client side to the server. So it's ACKed. The ACK has a sequence number of 7, meaning that, hey, server side, I'm waiting for, like, I got everything up to 7-1. I got everything up to 6 bytes correctly, and I'm waiting for the 7th byte, which is never going to be anyways, because I'm going to hang up the connection, disconnect. So that it's disconnect the reset ACK. You see that this is the disconnect sent, and it's sent from the client side 1.102 to 1.105, and that's it. So the connection is terminated here. So this is the flow of packets that you can see from Wireshark by applying the right filter. So I've just filtered everything on one of my, like if you go to capture to options, this is my wireless interface. So I can have a filter here that would just look at, I can just say host, this is the filter that I can apply here. So anything that comes from 192.168.1.102, just look at these. Anyways, I've done this before, and this is what I've collected. So we're going to try to cross-reference these timestamps here that the packets are received with the timestamps that I have on Tracecompass where different events happen, right? And show you how they correspond to each other. It's going to be an interesting observation. So here's Tracecompass. Without going into a tutorial about how Tracecompass works, I'm just going to show you how this TCP connection is going to be handled. So I'm going to come here, Control F, look for my thread NCAT. Basically, it found it, right? So I'm just going to, this is basically the trace I collected. I loaded it up in Tracecompass. There's going to be a separate video describing in detail how to do this. Okay. So let me just pull this to the side. Okay. So this is the NCAT thread. This is actually the server thread that I was creating on this server process, in this case, on this machine here. So 19433 is the PID and the TID as well. And this is the time where it was created. this is a visualization of all the events that are happening on all of these threads, all the threads that were running on my system. And here you can see the detail of those, like the name of the events. Anyways, so this NCAT, this thread, you see it becomes kind of like orange, if you may, from about this time. This is when the thread gets created. Now, if I zoom in, at first there's going to be a bunch of events. The blue ones are when this thread is running in kernel mode, meaning it's basically executing a system call. The green ones, intervals, are when this thread is running in user mode, which is executing but not a system call, right? So the first part is how a terminal, a shell, would actually execute a command and would create a process, right? I'm not going to go into the details of this one because it's not really related to the purpose of this video, but as you can see, the main thing is that the exec ve command is, system call has been called by this process, which essentially what it does is that it loads up the binary for NCAT and then starts executing it. So I'm just going to skip this part and go towards the end. As you can see, the server, after doing a bunch of things to set the process up, this is the part that the server code starts to execute. So we have the socket system call, because it's blue. The socket system call starts from here. If I go to this events panel down below, you can see that it's executing on CPU 6 at this time. This is the start time that that system call is made by the NCAT process entry socket. So we have a family 2 type 1 protocol 6, and you can actually refer to the manual page for this system call to see what these mean. But essentially, family 2 refers to the AFINet family, which is the IPv4 family. So it's requesting a socket to be created, an IPv4 socket to be created. And then it's returning from that with a value of 3. Now, if you do man socket and you look at the return value, you'll see that, let me show you here. Okay, so I say man sockets. And this is create an endpoint for communication. If I scroll down, the return value, yes, on success, a file descriptor for the new socket is returned. Okay, so here it's obviously a success. So return 3 is basically the file descriptor. So file descriptor is an integer that Linux kernel assigns to every file that it opens for a process. It's just an index. File descriptor of 0 is always the standard input, 1 standard output, and 2 standard error, and then from there all the other ones start. So anyway, so this is the file descriptor that's allocated to us, and then we set the socket options, and then we bind. This bind system call, as you can see, it's ran on file descriptor 3, basically binds that socket. So socket is just like a abstraction. It's like a data structure with a buffer and you know, everything. But you have to bind it, tie it to a certain network interface and port, which is the 192.168.1.105 IP address and 5000 port. So this bind does that, right? And then there's the listen call. What listen does is that it kind of listens on the socket that you created for any SYN requests, for any TCP connection requests to be initiated, and then actually responded to. So that's the listen. Again, that's run on file descriptor 3 and some other file control system calls that may do a bunch of flag sets or gets, which is not interesting for us now. And then eventually you do a select. Now, select is another system call, which what it does is that it waits on a number of file descriptors for read or write events or any other events, right? So it basically waits. Let's say you specify a list of file descriptors and say, wait for these to become available for reading, or wait on these file descriptors until they become available so I can write to them, right? So what's happening here is that you're running select. What the NCAT wants to do is that it wants to wait on the socket, which is basically the file descriptor number 3, to be available for reading from, because it's waiting for a connection request to come on file descriptor 3, which is the socket. So it's going to do a select on file descriptor 3 for read. Now, you can see here that the read FDS, this is the file descriptors that I'm waiting on for reading. It contains the value of 8 hex. Now, this is basically a bitmap of all the file descriptors that this process has open. So it only has 0, 1, 2, 3 up to this point, right? So it only has 4 file descriptors. Now, 0, 8 in hex is going to be 1, 0, 0, 0, 1, and then 3 zeros. So that means that I'm waiting actually on file descriptor 3, because the like starting from the least significant bit, 0 is going to be standard in, and then 1 standard out, 2 standard error, and then 3 is going to be the socket. So we have only 1 for the socket, and then the rest of the file descriptors have a bitmap of 0, meaning I'm only waiting to read from socket, the socket that I created with file descriptor 3, and that's it. And then you can see that the write FDS is 0. So this is when we actually go into action. Now, NCAT is actively listening and pulling the file descriptor, or basically doing a select on the file descriptor for any events to arrive. If we go like forward in time, at this point in time, you can see again, so NCAT actually is taken away from the run CPU, the run queue of the CPU, because it's blocked at this point. So it blocks, right? And if I go back here, there's a legend. You can see what these colors mean. Now this kind of orange color, or yeah, orange means that wait's blocked. So at this point, my process is going to be blocked, right? Because I'm waiting for something to happen. Okay, so yeah, obviously I'm waiting for that file descriptor to be able to be read. Something, a request coming there. Now here, the same select is being unblocked, right? Looking at the legend again, here we see that this is wait for CPU, this brown color. Why am I waiting for CPU here? Because although the SYN request has come, but I still need to wait. Now that the kernel detects that the SYN request came, right? So it's going to give me the CPU to run, give me being NCAT. So it's going to give NCAT the CPU to run. But there's a little bit of time before that can actually happen. So this is where I switch from waiting for, I switch from this orange, which is basically blocked, right? Waiting for my SYN request, to here, waiting for the CPU, right? And the amount of time I spent waiting for the CPU is only 25.7 microseconds, right? So I come to the select, and the select basically exits here with a return value of 1, right? Meaning that only one file descriptor has something interesting for me, right? Obviously. And then NCAT server would run the accept system call. Why? Because this is the SYN request. So it got the SYN, right? So it has to accept the connection, right? That's why it runs the accept. You can see accept on file 3, and the return value is 4. Now, if you go to the manual page for accept, which I'm going to do, man accept, you can see that it receives the socket, right? And then the return value is return value on success. These system calls return a non-negative integer that is a file descriptor for the accepted socket. Now, if you are familiar with TCP, then you would know that the server is listening on a connection, or let's say a listen socket, but then for any new connection request that comes on that socket, there will be a data socket created or a connected socket created, right? So this return value of 4 is the file descriptor for that socket. So there's a new socket created and it's assigned file descriptor 4, right? And this is the socket that we would be using for communicating data between the client and the server, right? Again, you can see that the S port, source port is 14615, right? This is the client. I'm going to refer you back to the Wireshark capture. 14615 is the client port, right? Let's go back here. And then IPv4 address, v4 address of the client is basically 192.168.1.102. This is where it came from, right? So this is what I'm accepting. So what happens here is after this, I run a close system call. Now, what the close does, and this is only specific to NCAT, in general, the server doesn't close the socket. But in this case, NCAT server only accepts one connection in this mode that I ran it. So whenever that connection comes, it will close the listen socket. So you can see that the close system call has been run on file descriptor 3, right? So meaning that the server is no longer going to be listening for any new connections, but it's only going to be working on the data socket. So I run a bunch of commands on this socket to basically get its flag or set some flags. And then once this connection is set up, right, I'll have to wait. So I have this connection set up. I have the socket set up. I'm just going to wait for something to either arrive on the connection or be typed by the user that the server would echo back to the client, right? Again, a select, right? But this time it's interesting because the select, right, is going to be waiting on actually more file descriptors than before. Now you can see it's not waiting for something to be able to write to, but it's basically waiting for being able to read from exactly 2 file descriptors. So this is 11 hex. 11 hex is going to be 1, right? And then 0, 0, 0, 1. Okay, so if you map it out, that bitmap means the first one is basically file descriptor 4, right? Because now, well, we have 4 file descriptors, right? Like the index, we have from index 0 to index 4, right? So this 11 hex means that file descriptor 4 has the bitmap set. So I'm waiting on file descriptor 4, which is my connected socket, my data socket. Makes sense because I'm waiting for something from the client side to show up. Okay. But well, I don't have the 8 hex here because I obviously closed file descriptor 3, right? But then if you look, the LSB has a 1 there. the bitmap for the LSP is 1, right? And that's file descriptor 0, which is standard input. And that's actually interesting because NCAT here would also wait for, like, if I run this, it would wait for input from the user through the standard input, right? So it's basically saying, hey, I'm waiting for either something to show up from the client side through file descriptor 4 or something to come from the standard input so I could relay it back to the client, right? Okay, so that's the select. So let's step back here a little bit and try to cross-reference the timings between these two, between the packet trace that I got with Wireshark and the event trace from the kernel. Now, let's see when we get the SYN. Okay, the SYN packet coming from the client side, we got it at 1434 10 seconds, and then 959 milliseconds, 833 microseconds, and 631 nanoseconds, right? So this is the SYN packet. Now I expect that when this select returns, sorry, let's go back there. Okay. NCAT. Sorry, I'm gonna go back here to see everything and then zoom in. Okay. So this is the first time the server listened on something. So yeah, okay. This is where the NCAT server thread is being unblocked by the kernel and waiting for CPU. This is probably where the SYN came. Let's look at the time. Well, the time is 14:34:10 961. Okay, 961 14:34:10 959 61 959. So that's 2 milliseconds. This SYN, I got it 2 milliseconds before the thread is being unblocked. So it's pretty close, right? But let's dig a little bit further. Let's see how this whole thing is unblocked, how this happens, why this happens. I'm going to show you something which is the resources view. And here what you can see is what's being run on any CPU core, as well as all the interrupts that are being triggered. Now, let me just zoom out a little bit. Now, you can see around this time, there is a soft IRQ, network receive IRQ being triggered, right? This means this is a soft IRQ. A soft IRQ is different from a hard IRQ. Hard IRQ is interrupt. Hard interrupt is the actual interrupt, but then the actual service to that interrupt, the interrupt handler does a little bit of things, and then but then most things are delegated to a soft interrupt thread, right? We can't really go into that a lot in this video, but I'll create a different video for that to explain how interrupt handling works. But this is just the gist of it anyways. So this is a network receive base. So it's telling us that something is being received, right? And then close to this, there's a hardware interrupt, RQ198, right? Which I think it's going to be the actual hardware interrupt for our wireless interface that got the packet, because I don't see any other interrupts here. And in fact, I'm right, because if you look here on CPU 14, when this mysterious interrupt IRQ 198 is triggered, a little bit after that, there is a kernel thread. There's a thread ran with the name of IRQ /198 IWL Wi-Fi, which is related to my Wi-Fi interface, right? So this would be the actual hardware interrupt. that starts everything, right? And you can see that here in the events panel, you can see that the IRQ handler entry, this is basically where the interrupt service routine, the hardware interrupt service routine is being executed. We enter the hardware interrupt service routine and then we exit from it. And that's very quick, only 3 microseconds. Yeah, microseconds. And the IRQ name is 194. The number, the name is IWL Wi-Fi. Well, obviously, surprise. And then Q11, meaning that my Wi-Fi card has several queues for receiving the interrupts. This is being received on Q11. Now, let's look at the more interesting thing here. The time, 14, 34, 10, 961. Okay, 961. And then 959.83, right? So it's pretty close. Okay, so let's continue with our first pass on the analysis of how a TCP connection is handled. This is where we do the accept and we finally wait on select to receive something. Okay, so the select, as I said, is unblocked here. And you can see that the select returns with the file descriptor 1, which is basically the standard input, meaning that there is something being typed, right? And this is something that I typed on the server side that was sent to the client. So immediately after that, we can see that, sorry, I'm having trouble zooming in. Okay, so there is a read system call. Now, the read system call, it basically reads from a file. In this case, the standard input, as you can see, the read entry has the file descriptor 0, which is the standard input, as the file descriptor. So it's basically reading something from the standard input. And the read finishes off with a return value of 6, which is, if you refer to the manual for read, it's the number of bytes read, which is 6 characters, HELLO, plus a return character. And then, as I said, some magic with the file descriptor flags. Not really that interesting for us here. And then we are actually NCAT, the NCAT server calls the send to system call. Now, send to, basically what it does is that it sends something over the network. In this case for us will be the hello character, the hello word, that phrase that we typed in. So you see that send to is being executed on file descriptor 4. The buff is basically the address of the buffer. Here it shows up as an integer, but this is actually like a hex. The hex would be the address of the buffer holding the string that's going to be sent. The length is 0 and some other information. Now this send to completes and it returns with a return of 6 because it sent 6 bytes. Now the time it took to run send to is 82 microseconds, and the negative is because I went from the end to the beginning. It's not really that important. Anyways, 82 microseconds to complete this system call, right? We'll go into a little bit of more detail about what happens when we run the send to, right? But anyways, you can type in, like if you want to know what a system call does, you can type in man send to, and if you're lucky enough, you'll get something. So send to the socket, the buffer, the size, and a bunch of other things. And then the system calls are used to transmit a message to another socket. Essentially, this is all it's doing here for us. Well, so that makes sense here. And then after that, it executes the select because now it sent something, so it's waiting. So it's done with this thing. The server is done. So again, it's going to call the select system call again on the file descriptors for like file descriptor number 4 and file descriptor number 0. File descriptor number 4 is the socket here. File descriptor number 0 is the standard input. So the server is again waiting for either something to be typed in or something to be received from the far end, being the client, right? So let's see what happens after this. Select, again, returns. So something has been received by the other end. It's waiting for CPU to be given to the NCAT process. Once the CPU is given, it will finish the select system call with a return value of 1, and you can see the file descriptor that has something to be read from is actually the file. This bitmap, if you kind of expand this bitmap, it's going to be 1, 4 zeros, right? So it's going to be the file descriptor number 4, meaning it's received something from the far end. Okay, so the select, this is some piece of data, for instance, or it could be, well, we'll realize what this is, right? In a little bit. But let's look at the time here and try to cross-reference this with the actual packet trace, right? So the select here, when it is unblocked, the time is 1434, 14, right? 748. 748, 748, right? It's pretty good match, right? 748, yeah. 748288, 748247. A little bit before that, we have this packet coming. What is this packet? This is a packet coming from the client to the server, and it's a reset ACK. It's a reset with an ACK, sequence number 1, yada, yada, yada. Basically, if you're familiar with TCP, this is a packet sent from the remote side, in this case the client, which would cause the server to close the connection. So this is basically the other side saying, oh, I just want to close the connection. So the client, in this case, probably did a Control-C or something that closed the connection, and that resulted in the in a reset TCP packet to be sent to the server, right? So the reason that this select is being unblocked is because it got a reset packet from the far end, right? And, well, not surprisingly, after this we have a receive from. Okay, so select figured out there's something to be received. Now the receive from system call receives something on the file descriptor 4, right? And when that's done, well, again, not surprisingly, there's a close. Okay, so the NCAT server actually figured that, hey, okay, I have to close the connection. So it calls the close on file descriptor 4, and that's done. So let's see what happens after that. Yep, okay, so actually exiting the process, I believe, exits here. And this should be the end of it, yeah, because after that, this whole thing is gray, meaning that there's like this process ended. That's it, because the server also quitted after realizing that the client quitted. Now, this is not normal behavior. This is just how NCAT server responds to a client hanging up. Okay, so we saw how a TCP connection passes through the kernel and the system calls that it invokes, and how that relates to the packet trace. And there was a very close match in terms of the timing between different events that were triggered, were seen on the kernel side, and the packets that were received, right? What I want to do next is to basically delve a little bit deeper into what these system calls are actually doing and what are the file descriptors and things like that. Let me just show you a few things, what I mean. Okay, this, okay, so let's look at one before this, the send to, okay? This is where I sent the hello text to the client. So I'm running the send to on file descriptor 4, right? Let's say I didn't know what was going on. I didn't know what I was tracing. I didn't have the packet trace. I had nothing. I had no idea what was going on, right? And I just wanted to know what this file descriptor 4 is. What is FD4 referring to? Now, FD4 is just an integer, and I don't know what it is, what kind of file it refers to. Is it a socket or just a normal file or what? It's just a number, right? It means that it's the 4th file descriptor that this process, meaning NCAT, has allocated or opened, right? That's all it means. There are these very nice LTTng events. They're called LTTng state dump. And if I show you my LTTng bash script that kind of I use to start LTTng tracing, you can see that again this whole LTTng will be addressed in a different video, but you can see that I've enabled a set of LTTng state dump underline star events, right? These are all the events that I've enabled. Now these events are very interesting because it tells you what are different, let's say, for instance, let's just search for it. LTTng, let's just see it, state dump, okay? Okay, and I want to search for NCAT. And in a different trace that I've collected, I've had this enabled, and we can actually look at it here. LTTng state dump, okay? So let's see NCAT here, 310, 310, okay? So 31020, there you go. Yeah, so we should have had an entry like that. For whatever reason, it wasn't there. Either I ran the experiment the wrong way, or I don't know. Since I don't want to repeat the experiment, I'll just show you from this previous trace that I had collected. Anyways, sorry for the bump here. Okay, so we can see that it has a set of events called LTTG state dump file descriptor, right? So it tells you what each file descriptor is pointing you. So here FD0, right? FD0 refers to /dev/PTS4. That's the standard input, standard output, and standard error for that particular process, because that was actually the terminal that I had all these running on, right? So it's, you know, those terminals or those devices in Linux refer to the different terminals that you have open. PTS 1, 2, 3, 4, different tabs, different windows of terminals. And then the file descriptor 3 in this case, which is kind of equivalent to the 4 that we had in the other trace that I collected, is basically referring to a socket. So it tells me this is a socket, right? This is a socket. Now, let me show you something with kind of a number here inside the brackets. So let me show you something. I have NCAT listening here. And if I do, let's say, so PID of NCAT, see what's the PID. Okay, so I'm going to go and say cat under proc file system for this PID 3370, and then FD all the file descriptors, right? Not actually cat, let's just ls, list all of these, -l. Okay, voila, you see that this is actually the list of all the file descriptors that are currently open for a particular process, right? And you can see that file 0 is file descriptor 0 is referring to PTS2, that's the second terminal. The standard output is again this terminal. Standard error is also again this terminal, because I haven't really redirected them, so they're the default value here. And then file descriptor 3 is referring to a socket. And this is just the inode number of the socket. And if you're familiar with Linux, you know that the inode is an index into the metadata for the file system. Okay. So going back to our analysis, all I wanted to show you here is that you can go from a file descriptor to what it actually is using the LTTng state dump events, right? So there's going to be one LTTng state dump event for every process, which will tell you basically a lot of information about that process, in particular what every file descriptor of that process is pointing to. And one important thing to note is that file descriptors have basically a process scope. So two different processes, right, can have the same file descriptor number, but they can assign to different files, right? The scope of a file descriptor is the process. So a file descriptor 2 in process 1 is unrelated to file descriptor 2 in process 2 or process 3. However, all the threads of a certain process have the same file descriptor naming. So file descriptor 10 in thread 1 is the same as file descriptor 10 in thread 2, in thread 3, so on and so forth. So that's something to have in mind. Okay, so let's go back to our NCAT here. So I just showed you that how you can figure out what each file descriptor is, right? So that you know, okay, I'm running a select on this file descriptor 3 here. What is that, right? Oh, it's a socket. Okay, so I know what I'm doing here. There's some network communication going on, right? Something else I wanted to show you here is actually what happens when I'm doing the send to, right? So let's see. Let's go to the part where we do the send to. Okay, send to, here it is. Okay, so I just want to know what happens. Now I select this part, corresponding part is highlighted here. Actually, what CPU am I on? I'm just going to hold my mouse here, CPU 6. So I'm just going to pay attention to all the events that are happening on CPU 6, right? So ignore the rest, just to pay attention to the events on CPU 6. I can actually, what I can do is I can just say 6 here, right? And I can actually apply the filter, right? And then I can go back and do the selection, right? And I should be getting, yes, this is the relevant part. Okay, nice. So what's happening? I get a system call entry. I enter the system call, and then here I exit from the system call. There are three interesting events in between these that tell me what's actually going on. One is net device queue. So this is telling me that there is a packet being queued into the network device. Then I have the SKB consume, which is telling me that the socket buffer, SKB stands for socket buffer, it's a famous structure in the kernel, is being consumed, right? And then I get the network device XMET, meaning transmit. So this is eventually when it's actually transmitted, right? So that kind of makes sense. The packet is queued, and then it's consumed by whatever, let's say, driver or something down there that needs to transmit it, and then eventually it's transmitted, and then we exit from the system call, right? So that's very kind of nice information that you have here. So let's try to see, try to cross-reference these times with the times that we have on the packet trace, right? So this is where I send the data. If I go to my Wireshark capture, here is where I do the data. I sent the data with a length of 6, right? So the time here is 1434, 12.275. So 12.275, 12.275. Well, actually, all of them are 12.275, so we're very close. Let's look at the microsecond part. 058. 054. There you go. 054, 062. So 058 is in between these two. So actually, the packet capture happens right between these two events, right? So the kind of the packet capture infrastructure or Wireshark is able to intercept this packet right between these 2 points. Almost, I can't say really in the middle, but close to the middle, right? Actually, exactly in the middle. And it's between the network when it's actually queued and when it's consumed, right? So it's kind of midway in the protocol stack. Now, I can actually show you the place in kernel code that this netdev queue happens. Now, let's just do that. Netdev queue. See how where these trace points are coming from. That's another level of detail that we're going to drill down into. NetDev queue. Okay, I have the kernel code here. Usually trace points, I'm just going to type it in NetDev queue, but usually what happens is, if I'm lucky, I'm going to get it, but let's take a look here. NetDev queue, that's a trace point, right? Usually what happens is that events in the kernel are prepended by a trace and then NetDev queue. There you go. This is not this is not 100% true, but it's true most of the time, right? This is where that trace point is triggered. So in the Linux kernel code here, in the protocol stack is where that trace point, whenever the kernel executes this line of code, you will see this trace point if you actually trace for it. How you trace for it? Here in LTTng, I'm saying, okay, intercept all net underscore star events for me, right? Including netdev queue, right? So netdev queue skv is the socket buffer, is basically let's say, the packet and the metadata, or the metadata of the packet that's being passed along the protocol stack, right? So this is where that is actually executed, and you can see what's going on if you want to scroll up. Anyways. Okay, so that's a piece of very interesting piece of information there. I hope you liked that one. So we actually drilled really, really deep down, right? What else? What else? Let's look at, oh, actually, what I wanted to show you. Yeah, let's look at something else. When we receive the SYN, right? Let's look at that. This is basically before all this happens. Okay, this is the accept. So when I run the accept system call, right, I'm actually accepting the connection from the other end. So this is where I have already received the SYN as a result of this select being unblocked, right? So the select was waiting on my file descriptor, my socket, to unblock. Basically, now what happened is that some packet arrived, so select unblocked, select exited, and because accept is being called after that, I know that this was a new connection request, hence a SYN packet, right? But where is that SYN packet? I want to know what happens here, right? Just like I did for the send-to, I just want to know, kind of delve really kind of into the detail as much as I can. Now, in this case, it's a little bit more tricky because this thing is not happening synchronously as the send-to did. Synchronous, I mean that, okay, send-to tells the kernel to send something, and the kernel immediately starts executing steps to send the packet. But in the receive side, whether it's a SYN or some other packet, the kernel is not really acting synchronously. It's just waiting, doing whatever it's doing, and this NCAT thread is blocked. And then all of a sudden an interrupt comes and asynchronously triggers a chain of execution that is responsible for handling the received packet, whether it's a SYN or a data. Okay. So I have to look for an interrupt. Let's do that. We want to know what kind of interrupt am I getting. Okay. So I probably got the interrupt when this thing got unblocked, right? So let's dig a little bit deeper. So before the select, right here, the thread is unblocked and put into the CPU run queue, waiting for the CPU, right? And this is actually run on what? On CPU 6, right? But if you pay attention, you can see that it's been, like here, it's been waked up. Like we get a schedule waking and then a wake up on CPU 14. From what process do we get it? From the IRQ/198 IWL Wi-Fi. This process, which the name shouts, it's related, it's actually the kernel thread responsible for handling interrupts coming on my Wi-Fi interface. Okay, so that thread is waking my server up. Most likely something has arrived on the interface and it's basically destined for this process NCAT, and it's just waking it up. That's what's happening. Okay, so let's track back and see what happened here. Before this, okay, so whatever happens is it's happening on CPU 14, and the context here, if you look at the context, it means that all of these events here, these events are happening in the context of this particular process being IRQ IRQ 198. Okay, so I better look for this thread. I can actually look for it here, or I can just look at the resources view and see what thread is running on what CPU. On CPU 14, this thread is running on it. You can see that, okay, yeah, there is a hardware interrupt triggered here. I know because I know the color codings. This is interrupt. There's a hardware interrupt. Okay, and then this guy shows up, and this is the software interrupt, right? Anyways, that's a little bit more detail to go through. In a few more minutes, I'll get to that. But I get the hardware interrupt, then I get that thread running, right? So here, again, I see that this interrupt line is being raised, right? And then this results in a network soft IRQ for network receive to be triggered. Well, this all kind of makes sense, right? I'm waiting for the SYN packet, right? So this happens. Now, this is not actually the SYN packet, but let's just assume for now that's the SYN packet anyways. So anyways, there's a packet arriving here, right? But let's just go through the flow. There's a packet arriving that is waking up NCAT, the server, okay? Let's just go through the flow. From here, if I start from here, actually I lost it, sorry. Again, Yeah, this happens from time to time. Okay, so select, and yeah, here it was here. This is the one that causes the accept to run, and I was here. Okay, so I'm getting waked up, right? But if I track this back, I see that there's an interrupt handler entry, right? This is the IRQ 198 is being fired, right? The name of that is IWL Wi-Fi, queue number 11, right? So the interrupt service routine is running. That interrupt service routine basically what it does is that it causes the scheduler, right? It causes the scheduler to wake up who? This kernel thread, which is in charge of handling my interrupts. Okay, that is waked up. So I do a sketch switch to that. Let's go to the resources view so you can track it. Interrupt handler entry. This is what we get. Interrupt handler exit. And then scheduler says, hey, wake up, this guy, this thread, your interrupt has arrived. And then it receives the wake up call, and then eventually the scheduler switched to this thread. Now you're wondering, why didn't it schedule switch to NCAT? Well, because there's a step before that. The interrupt has to be processed and then the packet handed over to NCAT. The interrupt is not going to go immediately to NCAT. The interrupt is going to be handled by a bunch of threads. Well, actually by a kernel thread in this case, the IRQ 198, and then that is going to prepare the packet and then call NCAT. Okay, so here the soft IRQ is raised. Soft IRQ is basically where the bulk of the interrupt service routine happens. The reason why we have a hard IRQ and a soft IRQ is that we don't want to, like, when you're handling interrupts, you're running in a very privileged state, very high priority, right? Hardware interrupts have the highest priority, and then the software interrupts. So because we don't want to have the CPU and resources busy when we're handling a hardware interrupt here from here to here, we actually delegate the processing. Like, we do a bunch of very essential things, minimal, and then we delegate the task to a software interrupt, which runs in a lower priority state. And sometimes that software interrupt, in this case actually, delegates that to a kernel thread, which is the IWL Wi-Fi that you see here. Anyways, so you enter processing that software interrupt, and then you basically entered it. This is the software interrupt service routine. What it's doing a network receive, right? And then the network receive ends, and then network interface receive socket buffer, right? Obviously, it's telling you that the buffer is received, right? And then it consumes it, right? This all makes sense. And then the network interface goes back into polling mode to see, oh, are there any more packets or not? And then that's the end of the software IRQ. And that's the end of this thread as well. So the thread has processed everything. It has consumed the packet. And by consuming the SKB, what it means is that it has now copied this into the socket buffer for my NCAT. So it has actually copied the socket and copied the packet that it has received into the file descriptor number 4, or was it 3? I don't remember, that the select for NCAT is waiting on. Okay, so the sequence of events is like this. You get a hardware IRQ, right? You service it, delegate to a software IRQ. The software IRQ is serviced. Basically what it does is that it receives, it forwards, it guides the packet and processes it through the network stack from bottom up, right? copies it into the file descriptor of the socket of the application, in this case, the NCAT server, that's waiting on it. And then once it does that, it's done, right? That's a done deal. Okay. So once this happens, where were we? Yeah, here. This is done, right? So I schedule out myself. And what we expect to see is we expect the select to return, right? Okay. So, however, this is not the result of like this is generally what happens, right? And this is probably what happened here for some other process, but for this select, this is not the reason that this select got unblocked. Okay, let's go back and see what happened there. Okay, so the question is, if this is not the SYN, then what is this mysterious interrupt for? Let's look at when this interrupt happens. This interrupt, or I can look at the resources view, happens at 10.961, 304, 10.961, 304, 10.961, okay, 304, pretty close here. What is this? This is the ACK. Okay, so this is basically, the TCP three-way handshake is that the client sends a SYN, the server responds with a SYN ACK, and then finally the connection is established by the client, essentially ACKing this whole thing and saying, yeah, I'm committed to it, right? ACK. This is what is sent to the server. And this ACK is fine. So the end of the three-way handshake is here. The only time when the kernel bothers to unblock the process, the server in this case, is here, because when the SYN is sent, the client may not still be committed to it. That part is handled by the kernel itself, right? So when the SYN is sent, kernel receives the SYN, responds with the SYN ACK, and then when the ACK comes, if it comes, then it means, yeah, the client is committed to it, so the server is gonna be waken up, unblocked, and the select, like this here, put on the CPU run queue, and the select is gonna finish off, right? So this was very interesting to see, because, otherwise you wouldn't know. Like there would be no easy way for you to know this, that the process is not involved in the three-way handshake, other than tracing or reading the code, right? Reading the kernel code. So yeah, this is when the process is said, hey, you're good to go, unblock and deal with this connection, accept the connection or whatever, right? So that's for one very nice observation that we saw here. I really like that. But let's say I had the question that, okay, eventually I want to know when this SYN happens, right? I want to see it in the kernel. This SYN, how does this SYN get handled or processed by the kernel on the receiving side, right? Well, there are different ways to tackle this, but the easiest way for me is that because I do have the packet trace, I'll look at this time and try to find whatever interrupt happens around this time. Okay, 10.959, okay? And usually interrupts from the same source, packets from the same source trigger the same hardware interrupt line. So if in this case, I was triggering interrupt 198, this interrupt, right? IRQ 198, if I scroll down, 198, right? So I should be looking for another interrupt 198 around the time that is here. 10.959, okay? So I go back and I try to zoom out and see, yeah, okay, so I see something here. I zoom in, look at the time, and voila, it's 959, 768, 768, here 833, a little bit after that. Makes sense. I bet you this is the time when the SYN is received. So let's look what happens on the CPU here, right? Okay, so this CPU, in this case CPU 14, is the one, again, that receives the interrupt. If you look at the events here, now I'm going to only look at whatever's happening on CPU 14. And let me just do this one more time. Yeah, okay. I enter the hardware interrupt service routine. This is a very quick routine. Takes only what? 4 microseconds to execute, right? And then it wakes up this IRQ server thread, right? It wants to delegate the task to this one. So it's waking it up, right? And it raises the soft IRQ for vector 3, which is the network receive IRQ, right? So it's doing a receive again, yeah. And then I'm getting this net receive entry and exit, right? But let's look at what this is about. This is the buffer that holds the socket, the packet basically. Here I exit from that, and then I do network interface receive escape buffer. Again, this buffer thing, 52. Okay, length of 52. Name is my wireless device. Oh, it actually tells you that the network header type is IPv4, right? And this is getting interesting. A bunch of information from the header, fragment, offset, whatever, TTL, protocol is TCP. Oh, okay, getting more interesting. And the checksum, source address, padding, no, actually, yeah, source address is 192.168.1.102. This is the client address. Let's go back to here, Wireshark. Client address is here. That's the source address. Same thing here, okay? Same thing here. Oh, sorry. Yeah, this is the source address. And this is the destination, which is the server, which is me. Again, that was the IP header. This is the TCP header. Source port, destination port. Makes sense, right? And then flags, right? Flags is 0x2. Now these flags tell you if the packet is an ACK, is a SYN, is a what, right? So I'm just going to go and check out this flag 0x2. Actually, here I'm going to look at the transmission control protocol. Flag is 0x2. That's the 2 hex, which is SYN indeed, right? Okay, so it checks out. That's the SYN packet. There you go. You have it there, right? So that was very interesting for me, like very exhilarating to see how this happens. So this is actually the SYN packet. This is when the SYN packet is consumed in the protocol stack and then eventually queued, right? And then eventually, actually, this is where it's received, queued, and consumed, right? So the time that it is consumed is 959,929. So let's see, 959,833. Okay, so somewhere around a little bit after this is where I get those like other events. Anyway, so the timing is right. Now, something interesting is that immediately after consuming, you see the net device transmit. What is this? This is telling me, oh, okay, I'm transmitting something right after. So immediately after that, like what? Okay, from here to here, 17 microseconds after consuming that SK buffer in the kernel, I mean, not by the application. Oh, the application is never going to see this, right? It's the SYN. I'm sending something, right? So this is this transmit chain. What is this? I know what it is. It's the SYN-ACK. It's the response to the SYN, right? It's the response to the SYN that the protocol stack does it by itself without involving the application. Again, something interesting. And the timing is 959,927. Okay, 927. 929, you see? The transmit is here. So that was 927, this is 947. So a little bit before that, right? Timing is fine. And yeah, there you go. Okay, so I guess that's all the interesting information that was here. And the software IRQ exits eventually. And this is basically the next interrupt, which is the the ACK. This is the one that is eventually, this is the next interrupt. This is the one that unblocks the server. So let's go over this one more time, right? Okay. Here, I'm gonna go over it from this view. I hope you can see this. Let me see how much I can zoom in without losing this, like without going out of scope. Okay. Yeah, well, yeah, that's nice. Okay, so this is how things happen. A SYN arrives, triggers a hardware interrupt on IRQ line 198, right? That raises a soft IRQ, is raised. So it delegates to a soft IRQ. That delegates to my kernel thread responsible for handling the software interrupt. And what they do, all these software interrupts and everything, what they do is that they go through the protocol stack trying to kind of process the incoming packet through the protocol stack and consuming it, eventually copying it, well, if required, copying it to the application. In this case, the SYN packet is not going that way. So the response is immediately, the SYN ACK is sent back to the application. Now, it takes a while for the client side to respond with an ACK. Actually, you can see the timing, right? So from this whole thing finishing until the ACK coming, there's 1.3 milliseconds of delay, right? Here, the ACK comes, and again, this whole round of delegation to soft IRQ and the third kernel thread, is done. And if I go above, you can see that right when this finishes, the interrupt finishes, the NCAT process is unblocked because it was in the select. It was blocked in while executing the select system call on the file descriptor belonging to the socket. It is unblocked because now this packet that came from here, this path, has been copied. It's being consumed and copied into the file descriptor that select is waiting on. So NCAT is unblocked, select finishes, it doesn't accept for the connection is established, and then it waits for either something to be typed in or another packet to be sent from the client side, right? So what happens next? Actually, I shouldn't do it here because this is the view from the CPU, right? I should go to the thread view, which is here. So after this, it's unblocked again. I go to resources view, right? NCAT is unblocked here. I bet you there's going to be an interrupt here on line 198. Let's just zoom out. Oh, actually, in this case, it's not because, oh, I remember now, because it's a send to. So this is the select is returned because there's an input to the standard input file descriptor, right? So it's how do I know that? I went over this before, right? So it's going to send something. So there is no interrupt here, right? Because I'm just sending something that is being typed in. So I just go over this one more time. And then after I send it, I'm just going to wait, right? And then here I'm unblocked, received something from the far side, go back here. Yeah, there you go. That interrupt 198 is again here, and that 198 is causing this whole chain of delegation to happen. The interrupt is processed, the select is unblocked, and then I receive the Control C basically, or like this is the reset. So this is where the connection is reset. I'm receiving this, and I'm closing the socket, and I'm exiting. Now I'm here on CPU 6. So let's see what happens from in the receive from. So in the receive from, well, actually, I'm just receiving some. Yeah, okay. So, well, the receive from is not doing anything very interesting. It's just receiving something. Let's see if we can find something interesting happening on the interrupt side when it's actually processing the packet through the protocol stack. Let's see. Okay, CPU 14. Right. Yeah. Okay. It's receiving the packet, right? And then network interface receive SKB. Oh, but this is an IP version 4 packet. Let's see what the packet is. It's coming from the client to the server, right? And the flag is 14, right? Let's see what 14 flag means. Here, flag is 012. Actually, this is a little bit different from what I have here. Yeah, 0x14. This is 0x12. So this is a SYN, right? This is reset, and this is an acknowledgement. Okay, well, this is kind of weird here, right? Because I'm getting a flag 12 here, and then over there I'm getting a flag 14. I can't really figure out why this is the case, but what I see here is that it's telling me this is a reset, right? Oh, sorry, my bad. I was pointing on the wrong packet. This is the packet. Yeah, there you go. The flag is 14, right? Checks out. Fine. Okay. So that was the end of the connection, right? That was the end of the connection. And you can actually do the same to and see the ACK packet. This ACK packet is also very interesting. It happens around, yeah, 12.326. So let's go here, 12.326 control flow view. Let's just take a look at that as well. 12, well, I'm just going to type it here, 12 dot, search for it, 12.326. 326. Let's see, we should have a bunch of these. Oh, actually, okay, no, not this one. Okay. Actually, I'm just going to narrow down my search like that. This is not good. Okay, this one. There you go. Yeah. Okay. Let me go to the resources view and see what I have here. Any possible interrupts happening? Yep. There you go. Now I'm getting good at this, right? I bet you this is the ACK, right? Look at the time. 326, 376. 326, 432. So this is a little bit after that, which makes sense because the hardware interrupt is the first thing that happens. Okay, so this is going to be the ACK. Again, it's on the same IRQ line, probably from the same application. That's the hardware IRQ. Again, this round of delegation and whatnot is happening. If I follow it, okay, receive, network interface, receive, socket buffer, but what is this? What is this? Okay, this is coming from the client. Yep, that's the address. This is to me, that's my address. TCP port, that all checks out, and the flag is 0x10. Okay, what is this? 0x10. Let's see. I'm telling you, this is the ACK. There you go. That's the flag, 0x10. That is the flag. That is the ACK. the timing checks out, right? 326432, 326432. The time here is 326434. There you go. Just 2 microseconds discrepancy, right? So that is the ACK. Now let's see what's happening on the application when it receives the ACK. Okay. If I just zoom out a little bit, or actually I can go to the control flow view and look at NCAT. Well, NCAT is here, right? NCAT is here. And if I zoom out, can't really see anything happening on the application. So this NCAT is idle. No matter how much I zoom out, nothing really happens. Here, there is something, but this is way before that. So this is 12.275, but this is, this is 100 milliseconds after that. So this can't be related to that, right? Again, go here, that's where we were. Okay, again, you see that the ACK has arrived and the kernel is entirely taking care of it. The TCP implementation is inside the kernel, and that entirely takes care of the ACK. If the application had any packets to send, right, it would have been notified, right? But it didn't have any packets to send, right? Because it wasn't really blocked on sending anything, right? So there was no reason for the kernel to wake it up. If the ACK had failed and there was a timeout, it would have probably woken it up, or maybe no, maybe it would have handled retransmissions. Well, that's for another experiment to find out. But anyways, this is actually the gist of what I wanted to explain about how a packet is handled and a TCP connection is handled through the kernel. Let me see if I wanted to, yeah, okay, let's look at a few interesting metrics. So let's look at how much time it takes from when you get the SYN to the acceptance of the connection, from the SYN interrupt to the TCP accept of the connection. Okay. Let's go back. This is, I think it was here where we had the accept. Yeah, this is the accept. Okay. If I go back to the resources view, I know that it wasn't this interrupt, it was the interrupt before, right? So I'm just gonna go from here to here, right? And then that time is basically the time from where I do the accept. Actually, it's the beginning of accept, so I might have I should have taken the end of the accept, but anyways, just ignore that for now. That time is 1.7 milliseconds. So from the moment that it receives the interrupt for SYN to the point that the connection is actually accepted, and which actually means that there are a bunch of other packets going back and forth, is 1.7 milliseconds. That could be a metric of interest, right? And something else, well, yeah, duration of send to, we saw that. Maybe you would want to know how much time it takes from send to the ACK that comes back, or how long a select call was blocked, right? Or how much time does it take to process an interrupt? Let's just take a look at this. Okay, so from the moment that the SYN arrives until the SYN is eventually processed, which is here, right? That is 197 microseconds, 0.7, right? So it's a little bit less than 200 microseconds to process a packet up from the interrupt, from the hardware interrupt up to through the protocol stack. Now this packet is not delivered to the application, but well, that's so this is just from the interrupt to when the kernel is done with it, right? So these are very nice metrics that you can find out for yourself. And yeah, one other interesting piece of information is that if we go and check out cat proc net TCP, this is interesting. You can see that this is basically, you saw this inode number, right? The file descriptor that points to this. Let's say you wanted to know, okay, let me backtrack a little bit. You remember when I said how you can relate a file descriptor to what it actually is in the real life, right? Using LTTng state dump events. So here I showed you, these are the LTTG state dump events, and this is the file descriptor. File descriptor 3 is pointing to socket this, right? Let's say I want to know really what this socket is. Now, okay, you told me that this is a socket. Good, nice, but I just want to know what this socket is. Now, if, and this is a big if this connection happens to live still after the tracing has happened, right? Or maybe if it's not living, you can take a snapshot of this file that I just dumped to the screen, this one, while you're doing the tracing. But anyways, if you have that connection, right, you can find the source destination pair, address, IP address, and port belonging to that socket and inode number, right? How? By going to procnet TCP file and catting that file, which basically reads the inputs and reads the contents of that file and puts it. And these are actually not files. These are pseudo files. These are not stored on disk. These are information prepared, statistics prepared by kernel and made available to any process through an API, which mimics the file API, so you can read it. Sometimes you can write it, but in this case, you can't really write it, so we can just read it, right? So what I can see is that I can see the inode here. These are all the sockets, right? These are all, so I have 16 sockets, TCP sockets open, and these are the inode numbers. This inode number is for another instance of NCAT that I'm currently running. That's not the instance that I used for tracing. So 497 is this guy. There you go. So it tells me that it's from that IP address and port number to this IP address and port number, right? This is the local address and this is the remote. Now, because there's still no client connected to this particular instance of the server, because I just ran this server standalone and haven't connected the client to it, the remote address is 0, right? But the local address is this guy. And these are in hex, by the way. So let's say I want to translate these to decimal. So there's my calculator. There you go. 5,000, port 5,000. Makes sense, right? Rings a bell because I am actually listening on port 5,000. And then here, 192, 168, 43, 65. So let's see. Sorry, here. And it was this guy. Okay, so 41. 41. Well, this is definitely the IP address, but then let's see what that is. So 41 hex is 65, right? It's basically from the least significant, right? 41, and then 2B, 43, right? A8, 168, and then C0, 192. There you go. So now I have a way to go all the way from my file descriptor number, right? Let's say file descriptor number is 3, right? Okay, that 3, I look it up using these LTTng state dump events, points to socket with this inode number. I go to cat procnet TCP, find that inode number here, and see what's the local address, what's the remote. That tells me what I'm really up to, right? Well, I have the transmission queue, receive queue size, and everything, but like the current occupancy, but that's not what I'm looking for right now. Okay, so I guess that was a lot of information to actually put into these videos, but I couldn't really find a better way to go through all of the details and still keep it short. I tried to be as exhaustive as possible, and I hope you've enjoyed this video. Stay tuned for more videos where I would explain how to use LTTng and Tracecompass, and in a separate video I would explain about the proc file system related to network. One of the examples is this one, and in another video I would explain the whole interrupt service, interrupt handling of the Linux kernel, and how in particular the network interrupts are handled. I hope you enjoyed the video. Please subscribe to my channel if you find it interesting, and thank you very much.